Let us now discuss the operating characteristics of various DC motors. So what is meant by operating characters here in case of motors? So we will be discussing the variation of speed as well as torque with respect to current as well as speed versus torque. We will start with the shunt motor. So the shunt motor and the separately excited motor are going to have more or less similar operating characteristics. Alright. So you can write shunt motor or separately excited motor. This is because the only difference between the two is what? The field excitation. And if the field excitation magnitude, if you are keeping both of them equal, then their operation is more or less similar. Right? That is why they are going to have the same operating characteristics. First we will see the variation of speed with respect to the armature current. So let us first draw the shunt motor. How does it look like? The armature is going to be here. The field winding will be in shunt and here you have the supply. The current coming through here we will call it as the line current or the supply current. This will be the armature current and this will be the field current. Now the terminal voltage if you take as V, the back EMF you can take as EB. Now we know that the back EMF is equal to K phi omega, where K is a proportionality constant, phi is the flux of the field winding and omega is the speed in radian per second, angular speed. Okay. Now EB you can write as what? V minus IARA, the terminal voltage. So you can write VT to be more clear. VT minus IARA is equal to K phi omega. So here you will get a relationship between the speed omega and IA. Okay. So omega you can write as 2 pi n by 60. Here omega is in radian per second whereas n is in revolutions per minute. Okay. So 2 pi n by 60 will be equal to Vt minus IARA divided by K into phi. So from here you can see that as IA increases, what will happen to the speed? If IA increases, then this term will reduce. So speed will reduce. So speed is going to reduce. But this is provided that the other terms remain constant. So K and RA anyways they are the machine constants. So Vt and phi should remain same. So provided Vt and phi remain same. Okay. So the plot is going to look somewhat like this. So here we will plot the speed and this is the armature current. Then you're going to have something like this. Okay. This is how as IA increases the speed will keep falling. Now one thing that you have to remember here is we have not considered the armature reaction here. So you can write this is without armature reaction. Now what will happen when there is armature reaction? So we know that the armature reaction is caused by armature current, right? IA. So if IA increases then armature reaction will also increase. Now what effect does armature reaction have on the field flux? It has a demagnetizing effect, right? Flux weakening effect. So field flux weakens as IA increases. And what is field flux? Phi. So phi is reducing. So now we have seen here that IA as IA increases the speed decreases provided Vt and phi remain same. But in armature reaction what is happening? The flux is reducing. So as IA increases, flux is not constant in reality but it is changing. Okay. So because of this what will happen? As the field flux decreases, then you can see from the expression here what is the effect of change in flux on the speed. So you can see that they are inversely proportional. So as flux increases, speed will reduce. As flux decreases, speed will increase. So now what will happen? As armature current increases, armature reaction will increase. Here you write this increases. And the field flux will as a result weaken. Now when field flux weakens, this will lead to an increase in speed because they are inversely proportional, the flux and speed. So if this is the characteristic without armature reaction, then with armature reaction, you're going to see a slight increase in the speed. Okay. So this is with armature reaction. Okay. So what is this value? This is the value of speed when the current is 0. So in this expression, if you substitute IA is equal to 0, then what is the expression for N you have? That is what you're going to get here, which is Vt by K phi into 60 by 2 pi. Now next is torque versus current. Torque versus armature current, IA. Okay. So what is the relationship between the torque and armature current? T is equal to K phi into IA. So here we will take K dash to differentiate between the constant that we used for back EMF. So now phi is a constant, right? If we don't consider the armature reaction, then phi is constant for a shunt or a separately excited motor. So what are you going to get here? T is proportional to IA provided phi is constant. Okay. So then what will be the characteristic? You're going to have a straight line which is passing through the origin like this. Okay. So remember, this is without armature reaction. Now what will happen when we consider armature reaction? So we know that as the current increases, the armature reaction will also increase. As armature reaction increases, the flux will reduce. Flux weakening effect of the armature reaction. So when flux increases and decreases, then what will happen to torque? Since torque is proportional to the phi as well, T also reduces. Okay. So this is without armature reaction. With armature reaction, it will slightly fall downwards. Okay. So you can draw something like this. Okay. So this is with armature reaction. So in both the cases, we have seen the relationship between the speed and armature current as well as torque versus armature current. We have first seen the relationship without armature reaction, and if armature reaction is present, then what will be the relative effect, right? Using that funda, we have drawn the characteristic for with armature reaction as well in both the cases, speed versus IA as well as torque versus IA. Next, finally, we can see the speed versus torque, N versus T. So we have already found this expression omega is equal to Vt minus IARA divided by K phi. Now instead of phi, you can write as Vt minus IA, you can write as torque divided by K dash into phi into Ra divided by K phi. So what you're going to get here, omega is equal to Vt by K phi minus T into Ra divided by K into K dash into phi square. Okay. So from here you can see that as torque increases, the speed will reduce. So the characteristics is going to be something like this. We will take the speed here and torque here. So as torque increases, what is happening to speed? It is reducing. Okay. So this is without armature reaction. Now what will happen when there is armature reaction? We know that as armature reaction increases, the torque will increase while the speed will decrease, right? So now as torque increases, this means that in this direction armature reaction is increasing. So that means speed will decrease. Okay. So how will you draw here? Relative to this is the graph. Now the effect we got because of armature reaction is that speed is decreasing. So we will draw the plot like this. Okay. So this is with armature reaction. Next we will see the case of series motor, DC series motor. Okay. So we will start with the speed versus armature current characteristic. Okay. So if you draw the series motor, there is going to be an armature here. Now the field winding is going to be in series. Okay. So here the armature current is equal to the line current or the supply current, and the terminal voltage if you take as VT, and the back EMF you are taking as EB. Then what expression you are going to get? EB is equal to VT minus IA into armature resistance as well as the field resistance. Okay. So RSE, series field resistance. Now what is EB? It is equal to K phi omega. So this is equal to VT minus IA into RA plus RSE. But also here in the series motor, we know that the field flux, that is phi, is going to depend on the amount of current that is flowing through it. So you can say that phi is proportional to the armature current. So we will write phi is equal to some constant Kf into Ia, and that is what we are going to substitute in this expression. So then what you are going to get? K into Kf into Ia omega is equal to Vt minus Ia into Ra plus Rse. Okay. So from here omega is going to be equal to Vt by K into Kf into Ia minus Ra plus Rse divided by K into Kf. So this here anyways it is a constant. So you can see that omega is inversely proportional to the armature current. So what will be the characteristic that you are going to get? This you can take as the armature current, and here you can either write angular speed or the speed in revolutions per minute. Now the plot is going to be something like this. This is what you get when there is an inverse relationship. Okay. Now one important thing that you can observe from this characteristic is that when the armature current is very small, the speed is going to be dangerously high. You can see from the expression itself. If you substitute Ia is equal to 0, then omega will tend to infinity, right? So omega will have, the speed will reach a very high value, which is very dangerous. That is why they say that the series motor should never be operated under no load. So you can write this: series motor should never be operated at no load. That is Ia is equal to 0, because at this Ia value speed will become dangerously high. Okay. Now what about the case of armature reaction? Here armature reaction will not matter, because in the previous case, in the shunt or separately excited motor, we were taking the condition that phi is constant, right? But phi is in fact not constant because of the armature reaction. Here phi is anyways not constant, it is changing with the armature current. So the armature reaction effect we don't have to consider once again. Okay. Next, what about the torque versus armature current, T versus Ia? So here what is the relationship between T and Ia? This is equal to K dash into phi Ia, but we know that phi is dependent on the armature current. So we have taken this as K phi into Ia. So you will get T is proportional to the square of the armature current. So previously it was a linear relationship. Here we have a quadratic relationship. So this is T and this is armature current. So how is the characteristic going to look like? It is going to look like this. Okay. So it will increase at a faster rate as compared to the linear relationship in the case of shunt and separately excited motor. And next finally the speed versus torque characteristic, N versus T. So we have already seen that omega is equal to Vt by K into Kf into Ia minus Ra plus Rse divided by K into Kf. Once again, armature current, instead of armature current, you will write in terms of the torque. So Vt by K into Kf into Ia is going to be T by K dash into Kf minus Ra plus Rse divided by K into Kf. So you can see that here the speed is inversely proportional to the torque, not just inversely proportional but inversely proportional to the square root of torque. Okay. So you can write here omega is proportional to 1 by root t, because this here is a constant. So the characteristic you are going to get, this torque if you take and this is speed, then you are going to get the characteristic like this.